In this demo, you'll find out whether k-means clustering is a good technique to use to classify MNIST handwritten digit images. Clustering is often a preparatory step to classification algorithms. You'll cluster the data into logical groups and then perform prediction on input data to see which group they belong to. Let's look at a more interesting k-means clustering problem. This time we'll perform clustering on the MNIST handwritten dataset. Once we've performed clustering, we'll try to see if we can use these clusters to predict the label of an input digit. The imports are the same here. Use the TensorFlow library function to download and get the handwritten digit images. We'll get training digits, training labels, test digits, and test labels. We use a very small number of test digits because we are going to manually examine the output of our k-means clustering when we use it for prediction. Because we are working with images, set up a helper function to plot an image to screen. This will be displayed in line. Display one of the training digits to make sure this function works. And then let's go ahead and start with our k-means clustering by importing the right TensorFlow libraries. Set up the input function that we'll use with our k-means clustering estimator. The code for this is exactly the same as we saw in the last demo. This time, the input argument digits is a one-dimensional array representing an MNIST handwritten digit. Another important point to note here is that because clustering is an unsupervised learning algorithm, even though we have labels associated with our training dataset, we don't specify the labels in this input function. Labels are set to none. Instantiate an estimator for the k-means clustering algorithm. The number of clusters that we'll use here is 10. Now, 10 is an obvious choice here because we know that there are 10 possible choices for digits from 0 through 9. It might be interesting and something for you to try out on your own. Increase or decrease the number of clusters and see how the prediction capability of this algorithm changes. If you specify fewer clusters than 10, then not all of the digits will be represented. You won't be able to predict all digits from 0 through 9. If you increase the number of clusters, then some of the labels will be repeated. We'll call estimator.fit to train the estimator as before. Once again, clustering is an unsupervised algorithm. There are no labels, or we don't make use of the labels to go along with the digits that we feed in to this estimator. We run training for 100 steps and pass in the training digit images. Once the training process is complete, you can call k-means estimator.clusters to get the cluster centers. Now remember though that these cluster centers are basically images. They have 784 pixels. They are 28 by 28 images which form the average of all the MNIST handwritten digit images which are part of that cluster. Every image has a dimensionality of 784, that is 28 by 28 pixels, which means every cluster center will have the same dimensionality. So instead of just viewing the actual matrix, let's display the cluster centers in the form of images. There are two specific points of interest that you should note here. If you look at the numbers represented by these images, you'll see that not all digits are represented. For example, the digit 7 is not present as a cluster center at all. That means when we use this clustering algorithm for prediction, you'll never get a predicted output of 7. The numbers 2 and 4 are also not represented. Now, depending on your training data set, when you run this code, you might find that certain digits are not represented as well. Another point to note is that these are not actual images from our training dataset. If you remember, the centroids of clusters need not be actual points in our input data. Similarly, these are not actual images. These are just images that we get when we calculate the centroids of all images within a cluster. We now want to use these clusters to see if we can predict the label for any input image. This is something clustering is typically used before classification, and that's what we are going to try out here. Now, what are the labels that are associated with each of these clusters? We can simply look at an image and manually figure out what the labels are by seeing what the digit looks like. For example, the very first image looks more or less like a 9, so that's the label that we'll assign to the first cluster. The second digit looks more like a 1 than anything else. So 1 is the label for the second cluster. The third digit is a little more difficult, but it looks more like a 6 than anything else. So 6 is the label that we'll assign. So go ahead and manually assign labels based on what you think the images look like. Now, I must give you a heads up that clustering on the MNIST dataset is really a poor way to classify the MNIST images. We've seen a lot of methods which work far better than clustering does. However, this code is particularly important in helping demonstrate how clustering can be used as a precursor for classification. Let's say your training data comprised entirely of unlabeled images. You couldn't use classification directly because there are no labels on which you'll train your classification model. One way to classify all the input data is to cluster them into logical groups first and then use the clusters to classify the input data. Let's take a look at the test images that we wanted to classify. Let's print it out to screen. There are just 5 of them after all. These are the digits, 4, 3 ones, and then a 0. Let's use these test images as an input, and using our k-means clustering estimator, let's predict what clusters these images belong to. Once we know which clusters these images belong to, we have the manually assigned labels to every cluster that we can use as our predicted label. Here are the cluster IDs for our test images. The first image belongs to cluster at index 7, the second to cluster at index 8, and so on. These are just the cluster indexes. The digits that are represented by these clusters are the predictions made by this k-means clustering model when we've used it for classification. Remember that we've manually set up the predicted labels in an array. We can simply iterate over that array and extract the predicted labels for our test digits. And the predicted labels for our 5 test digits are 6110. You can see here that it got 4 digits correct and the first digit wrong. It thinks the 4 is a 6. Now, this seems to be a pretty decent result, but don't forget, when we use this MNIST handwritten dataset with neural networks such as RNNs or CNNs, we get an accuracy of up to 98%. The accuracy for just these 5 digits is just around 80%. And you can try this out for yourself. The more data that you use within your training data set, the less obvious your cluster centers are. It's harder to distinguish digits within the cluster centers. Your model actually performs worse because clustering is not really a great machine learning model to apply for the MNIST dataset. In fact, clustering isn't really great for images because images have many complex features that CNNs work on well, but clustering really it's a very primitive model for very complex data. Our test dataset has just 5 images so that we could manually examine the prediction result. If you use a larger test dataset, then you'll want some helper function to help you display the accuracy of your clustering model for classification tasks. The input arguments to this function are the cluster labels, which we manually set up, the cluster IDs that we get from predictions, and the actual labels that we have available from the MNIST dataset. Get the list of predicted labels for the test dataset by using the cluster IDs. We use the for loop to iterate over the cluster IDs and use that as an index into our cluster underscore labels list, which we manually set up earlier. We can then count the number of accurate predictions that were made by comparing the predicted labels with the actual labels. Calculate the percentage accuracy and display it to screen. The test dataset that we have right now has just 5 images. We already know the accuracy is zero point 0.8 for these 5 images. We can use that to test that our helper function works correctly. And you can see that the number of accurate predictions are 4 and the percentage is zero point 0.8. Something for you to try out on your own. Increase the size of your test dataset and see how well your model performs. The performance of MNIST handwritten digit classification after creating clusters using the k-means clustering algorithm wasn't great. Images are complicated matrices and require specialized models such as the convolutional neural network. Clustering is not a machine learning model that is well suited to work with images. This is why, even if you have a huge training data set, you're not likely to achieve very high levels of accuracy if you use k means clustering followed by classification.